In this video, we would like to introduce flaretot, a complete solution for flare system design. Flaretot provides all the tools you will need to design, rate, and audit flare systems in one software solution. You can calculate performance of complex flare piping networks, including parallel headers and multiple flares. The flare loading from each protection device connected to the flare allows for multiple cases. Data for these cases can be easily calculated using comprehensive linked relief load calculations. The network loading and behavior can then be evaluated for all possible incidents using full case management. You can determine flare purge gas requirements using the calculator provided. But flaretot does not just model flare networks. It also allows you to calculate the impact of flares on the environment. This includes flare radiation levels, noise, pollutant dispersion, and heating of structural steel. Mitigating effects of shields are also included. Furthermore, since this is one software package, data required is linked to the flared gas, as calculated in the network. This means that data does not have to be manually entered from other software. This linked data approach also extends to the rigorous relief valve and rupture disk sizing modules included. Aside from sizing or rating, these relief valve and rupture disk modules include a rigorous relief installation piping rating using the Dyer's method. Depressurization of pressure vessels is also included in the blowdown module. This time-dependent calculation takes account of changing fluid properties in the vessel and transient wall heat conduction, and allows you to assess vessel safety during depressurization. Both minimum wall temperature during normal depressurization and potential wall failure from high temperature during fire conditions can be determined. Lastly, a module to size knockout drums is provided. The physical properties that are required by the network calculation and modules are provided by the integral component-based physical property module. In addition, various databases are provided throughout the calculations to assist with data requirements, for example pipe, control valves and wall properties. We will now show you all these features in more detail. A full graphic user interface is provided to define the piping network. To define the flare system, we just click on the required element at the top of the interface, and then drop it on the drawing. We use the Connect button to set connection mode. Then we simply click on the connection points to connect the units. The interface also supports copy and paste operations to speed up the build process. You simply select the units on screen, copy and paste them, and then move them to the required location. After connecting, in a few steps you have created a parallel train. To further speed up defining the piping network, flaretot provides a quick build header tool. The tool allows you to define a header in a few steps. Simply define the number of tailpipes and base tag, then where the header is to be placed, and finally the header pipe properties. This then creates a header arrangement with the majority of properties already defined. All the usual equipment found in a flare system is available for you to model the piping network. Flow sources to the piping network can be classified as generic: relief valve, rupture disk, blowdown valve with restriction orifice, control valve, manual valve, or restriction orifice. The source type is used to allow sorting within the case manager to make it easier to set up network cases. Each source contains multiple cases, which can be manually specified or linked to a relief load calculation. Component composition can be specified in mole or mass percent. The relief valve and rupture disk type incorporate device sizing, using the cases defined in the source. The network piping is constructed from pipes, tees, nodes, and manual valves. Pipe dimensions can be selected from the piping database provided, or derived using user-defined piping classes. These piping classes can be design-based, that is, based on material, codes, and allowable pressures. In addition, classes can be lists of allowable sizes, either selected from the database, or using custom sizes. Pipe fittings are also definable from the fittings database provided. The pipe pressure loss calculations allow for all phase types and pipe inclinations, and include the Dyer's method for accuracy. Tees, aside from calculating detailed pressure loss, provide a means to combine and divide flow. Nodes do not model pressure loss, but allow a combining of several flows. Manual valves can be opened or closed for all cases. These are useful for evaluation of proposed system modifications. Knockout drums are used to model removal of liquid. They also model the pressure loss over the drum nozzles and internals. The drum can be sized based on the flow rates through the drum when the network is solved. Liquid seal drums model pressure loss over the drum nozzles, as well as static pressure loss resulting from the liquid seal. They also model removal of liquid. Finally, either flares or atmospheric vents can be used as piping network exits. Data from both these units is linked to the atmospheric dispersion and noise modules, and in addition, flares provide data for the radiation module. The flare tip pressure loss can be calculated using one of three models: a basic pipe flare model, which requires only stack diameter; a multiple nozzle model, which also allows fitting of the coefficient of discharge to user rating data; a spline fit model, which uses rating data and rating gas properties to predict pressure loss at actual conditions. This model can be used for any special flare types. Pressure loss resulting from a purge gas seal can also be included. The pressure loss for the atmospheric vent can be modeled as a straight exit, 90-degree, or gooseneck exit. Wire mesh screens can also be modeled. After solving the network, detailed information on stream properties is provided. Key sizing criteria values for piping are also shown, including Mach number and density multiplied by velocity squared or cubed. You can also display key piping properties on the drawing. This visual feedback helps identify bottlenecks in the piping during design or rating. Notes can easily be added to the network sketch. You can choose any combination of engineering unit for all calculations. Also, you can change these units at any time. If you already have a model of a flare system, you may be able to import this into flaretot. You can import or export flare network models between flaretot and flarenet. You can also import stream data from process simulators. Flaretot can read files produced by HYSYS and Pro2. Data from PetroSim database files can also be read and imported. Flaretot includes a database of standard pipe schedules. In addition, any number of piping classes can be defined, which allow for automatic selection of pipe dimensions. Two types of piping classes are available. The first is a design class, specified from material, manufacturing data, and pressure, temperature design conditions. This class calculates pipe dimensions for any given nominal bore. The second class type is table-based, which can include any number of allowable custom or standard pipe sizes. Two typical design-based classes for flare systems are already predefined in new networks. Design classes can be converted into table-type classes and then customized. The design classes provide fairly accurate sizes early in a project, when specifications have usually not been issued. Piping can be sized using 4 sizing criteria. You can choose any combination of velocity or Mach number, density multiplied by velocity squared, or maximum pressure. The pipe size is automatically selected from the class to meet the criteria. This is an example of sizing 2 of the header pipes to meet velocity and Mach number criteria. flaretot supports full case management, from relief loads through to overall plant incidents. Each network source has multiple cases, based on a specified load or a linked relief load calculation. Calculations for fire, tube rupture or control valve gas blow-by are available. The source relief loads can be used to size relief valves and rupture disc installations. Source relief loads are mapped to plant incident cases by the case manager. Using this mapping, the flare piping can be sized for each plant incident case. This linked approach ensures that the effect of revisions to relief load calculations can be evaluated immediately. The dependent linked device sizing and network hydraulics are all maintained in a single network file. Each source to the network can have a number of relief load cases. Relief loads can be specified manually or derived from a linked relief load calculation. Relief loads are also used for relief valve or rupture disc sizing. Network relief cases are used to define a plant incident, for example, emergency blowdown. The flaretot case manager allows mapping of active source cases to each of the network relief cases. The mapping is clearly displayed on the case grid. The map is easily changed by clicking on the intersection of the network case and the source. The active case is then selected from one of the source cases. flaretot includes a component-based physical property module which generates all the data required for the piping network and calculation modules. This means you do not have to generate physical property data using other software. The physical property module includes over 300 standard library components. There is also full support for petro and custom components. These are easy to define from within the program, using minimal data. Components can be defined with as little as normal boiling point and specific gravity. The component definition is flexible. You can specify key properties like critical pressure, or select different methods for each property. This all helps improve the property prediction. You can also calibrate the temperature-dependent properties to ensure a more accurate prediction. We illustrate this with liquid viscosity. We have 2 values for measured viscosity. If we specify these, then the prediction is adjusted over the known range, improving the accuracy of predicted values. In addition to petro methods, the Joubak group contribution method can be used for estimating new component properties. The group counts are specified directly on a visual interface, which is shown here. The calculation modules complete the flare system design. These are linked to the data generated by the flare network model. We will present these modules in the following sections. Firstly, The flare radiation module. The flare radiation and temperature module calculates composite radiation from any number of flares on different stacks. This module also calculates the surface temperature of steel structures exposed to this radiation. Flare gas properties for the calculation are derived from the network. This means data does not have to be transcribed into this module, and so radiation can easily be calculated for each network case. The combined radiation can be calculated for any number of target points. Flaretot also includes a maximum radiation calculation for each point. This maximum occurs because of flame shape change with wind, and may not necessarily occur at the specified wind direction. You can produce contour plots of both radiation and surface temperatures in either plan or side views. All values are in real coordinates, and you can overlay the contour plots onto actual scaled images like equipment layout drawings. Radiation calculations use a detailed three-dimensional multi-point flame shape model. The radiation module uses an integrated mixed source model for radiation calculations. This model is a combination of the point IPS and diffuse IDS models. This improves accuracy near the flame. The weighting fraction of the two models can be user-defined. Heat fraction radiated correlations are included to provide estimates before vendor flare selection. Several methods are provided with a summary of results from all methods for comparison. You can size a flare stack height to meet a maximum allowable radiation value. Surface temperature calculations are linked to user-definable surfaces, so properties only need to be entered once. Supports variable emissivity with temperature. This is important for steel, as its emissivity varies significantly in the range of typical flare radiation and corresponding temperatures, and ensures a more accurate temperature prediction. Uses detailed calculation of natural and forced convection heat transfer coefficients. Next we examine the thermal effect module, which models structural steel temperature rise from flare radiation. The temperature module predicts the temperature increase with time for structural steel elements which are exposed to flare radiation. A detailed model is used which takes into account all radiation, heat conduction and convection effects. The model divides tubular elements into 4 quadrants to ensure more accurate modeling. The noise modules consist of a detailed atmospheric vent and flare noise module, as well as single calculations for noise from pipes and control valves. Next, we present the vent and flare module. The flare and vent noise module calculates combined noise from all selected flares and vents. The data required for each noise source is derived from the flare network. You can calculate noise at any number of specified target points. In addition, you can create contours of noise levels, using both side and top views. These contour plots can be superimposed on scaled drawings, like equipment layouts or terrain maps. HSE recommended noise levels are also provided in the default standard contours. Noise is characterized by different intensity levels over a frequency range. It is important to know this noise spectrum, since both atmospheric attenuation and the loudness perceived by the ear vary with frequency. Flaretot includes a typical flare noise spectrum. Vendor curves for actual flares can also be utilized. The frequency-dependent atmospheric attenuation is calculated using ISO 9613. Both A and C frequency weightings are reported. These weightings account for relative loudness perceived by the ear, as it is less sensitive to low frequencies. Note that A weighting is typically used for environmental and industrial noise. C Weighting might be used for very high noise levels. The noise module can size the flare stack to meet a maximum allowable noise level. Next, we examine the shield module. Here, you can define mesh and water shields. These attenuate both calculated flare radiation and noise, if the shield is active. The shield module is used by the flare radiation and noise calculations. Both fixed and water curtain type shields are supported. Any number of shields can be defined. Both flare radiation and noise attenuation are calculated. Noise reduction is applied by a frequency-dependent curve. Shield shapes can be defined using plane segments, which are rotated into three-dimensional space. Rectangular, circular, and polygon shapes can be utilized. The circular shape is usually typical of water shields. Any combination of basic shapes can be used to define complex shields, such as enclosures. Now we present the atmospheric dispersion module. The dispersion module calculates the combined pollutant concentration resulting from any number of active atmospheric vents and flares. Flares can be individually set to a burning or flame-out condition. In addition to pollutant concentration, percent of lower explosive limit is also calculated. Levels at any number of target points can be determined. Properties of each pollutant source are derived directly from the flare network simulation. You can generate side and plan view contour plots of pollutant concentration and percent of lower explosive limit. These contour plots are in actual coordinates. They can be superimposed on scaled drawings, like equipment layouts or terrain maps. For flaring conditions, the temperature of combustion products is calculated automatically, using a heat balance and by specifying excess air entrainment. A composite Briggs model is used to calculate the initial dispersion plume, taking into account buoyancy and momentum effects. A detailed Gaussian dispersion model is then used to calculate atmospheric concentrations. The wind speed at the required elevations is corrected from wind station measured speed. Dispersion is corrected for atmospheric stability, as well as for rural or urban conditions. The solar radiation, delta-T method, is provided to help calculate the atmospheric stability class. Next, we examine the purge gas module, which calculates required purge gas flow for safe operation at the flare tip. The required flare purge rate is calculated based on a maximum oxygen concentration of 6% at a distance of 25 feet from the flare tip. Three methods are used. The first is the original Heuser method as published in 1964. The exponent n, which is dependent on tip diameter, is calculated automatically. The second method is the modified Heuser method, based on a more recent modification by Heuser in 1977 to give more realistic values for the flow. The third method provided is the TAN method. Next, we examine the physical properties and unit conversion modules. These assist in providing engineering data for tasks outside flaretot. You can perform a three-phase flash for a given composition. 16 key total properties are reported, for example calorific value and dew points. In addition, 10 key physical properties for each phase are reported. You can create tables of physical property data for a temperature and pressure range. In addition to standard, dry hydrocarbon-based phase envelopes, you can create full phase maps. These consist of a color diagram showing single, 2 and 3 phase regions. The unit conversion module provides a tool for converting between a wide range of engineering units. Next, we examine the knockout drum sizing module, which allows sizing and optimization. A knockout drum sizing calculation is maintained in each KO drum in the network. The fluid data can be derived from the network for these calculations. In addition, you can have an unlimited number of standalone calculations. Sizing for both vertical and horizontal drums is supported. Horizontal drums can have more than one inlet or outlet nozzle. The required nozzle sizes are also calculated. The calculation provides an estimate of the required vessel thickness and shell weight. This estimate is derived from basic mechanical and design data. A database of typical allowable stresses is provided, so that it is easy to define the mechanical design parameters. For horizontal KO drums, a table of shell weight against the length to diameter ratio is generated. This allows a near optimum vessel cost to be selected, since there is a strong correlation of weight to cost. Next, we look at relief load calculations, as well as rupture disk and relief valve sizing. The relief load calculations determine required discharge to the flare network to ensure safe conditions during an abnormal incident. 3 types of calculation are provided: equipment exposed to fire, gas blow-by through a liquid control valve, and heat exchanger tube rupture. The calculations link to and provide data for the network source cases. This data can then be used for network hydraulics and device sizing. The calculations are thorough and examine the situation in detail. All physical properties are component-based. The fire relief load calculation determines the flow resulting from exposure of a system to fire. The system comprises a vessel and associated piping or equipment. The vessel can be a vertical, horizontal or spherical type. Connected equipment and piping is specified individually in a grid. These can be allocated to liquid or vapor phases, as well as with or without fire exposure. Standard vapor and liquid type API calculations are provided. In addition, a detailed heat transfer model is included. This model accounts for the different heat transfer coefficients in the wetted and dry vessel areas. It also models heat conduction through the vessel wall and insulation. The height of the fire can be specified, which sets the extent of vessel fire exposure. Only conditions at normal operation need to be specified. The calculation determines the system conditions at relief pressure. In addition, the time taken to reach relief pressure is calculated from the enthalpy change and fire heat input. This calculated time is useful, since it may be substantial for vessels with a significant volume of liquid, or especially water. The gas blow-by relief load calculation determines inadvertent vapor flow through a liquid level control valve. This usually results from control valve failure and loss of liquid level. The calculation uses component-based physical properties. The control valve rating calculation uses the ISA or the universal gas equations. Fittings attached to the control valve can be included. A control valve bypass valve can be included. This can be modeled with isothermal or adiabatic gas flow equations. A database of typical control valve and bypass valve characteristics helps provide estimates during preliminary design. The tube rupture relief load calculation models relief flow if a heat exchanger tube ruptures. It uses rigorous component-based adiabatic calculations to determine the resultant flow from the tube to shell side. The dias, liquid and ideal gas adiabatic models are provided. These cover all possible conditions, namely vapor, liquid and two-phase, including change of phase conditions across the tube break. In particular, vapor, including possibility of retrograde condensation. Liquid, including possibility of vaporization. And two-phase flow. In cases where vaporizing occurs as the pressure is reduced, vapor may not realistically be produced until after the fluid has left the rupture. This is because of the short residence time in the rupture exit, and can result in a higher required relief flow rate. This is resolved by including the liquid-only and Dyer's frozen models. Potential heating of the relief fluid by the shell side fluid can also be allowed for, which can result in a higher volumetric flow. Rupture disk calculations are linked to multiple relief load cases. These are either in a network source or in the unlimited standalone calculations. The calculation uses all selected cases to rate the rupture disk, so that the controlling case can be identified. Both the coefficient of discharge, Kd, and flow resistance, Kr, methods are provided. The Kd method rates only the bursting disk as a nozzle, using the discharge coefficient provided. The Kr method rates the pressure drop over the whole installation, using the calculated flow resistance of each element. Our flow resistance calculation uses a sequential analysis of the disk installation piping and fittings, etc. This provides a more realistic pressure loss, compared to using a combined K value. This is especially true where higher loss elements are installed near the exit. The API example for vapor, which does use a combined K value, is also included for completeness. The pressure loss over the pipe entry from the vessel is implemented according to the Dyer's procedure to account correctly for the area reduction. Pressure loss for all phase types is addressed with the adiabatic ideal gas, incompressible and Dyer's methods. The Beggs-Brill method is also provided in conjunction with Dyer's for hold-up and two-phase friction factor for all pipe inclinations. All methods can be used simultaneously for comparison. The pressure profile for the Kr method can be viewed in chart form to identify bottlenecks. Relief valve calculations, as in rupture disk calculations, are linked to multiple relief load cases in network sources or in standalone calculations. The sizing supports, as Me8, multiple set pressure arrangements, and supplemental fire valves. In particular, it addresses the different set pressures required for the valves, the increased relief overpressure, and fire case selection for supplemental fire valve sizing. BS5500 is also supported, which has different allowable relief overpressures to as Me8. The Dyer's method is provided to size the relief valves. This consists of a rigorous integration of the momentum balance equations, in conjunction with the physical property simulator. It is suitable for two-phase sizing, but you should note that the underlying equations apply to all phase states. Therefore, this method can also be used to provide results for gases, without using ideal gas assumptions, as used in the API sizing equations. Furthermore, the Dyer's method does not require simplifying assumptions, as in the omega method as presented in API 520. In addition to the HEM homogeneous equilibrium model, the frozen equilibrium model is provided, which can give more realistic results for vaporizing liquids. All API 520 gas and liquid sizing methods are provided, including liquid with capacity certification. Has support for editions 6, 7 and 8, for basis of ideal gas specific heat ratio. An API 526 database of allowed relief valves by set pressure and operating temperature is provided. This fully integrates with automatic and manual valve selection. The module uses smart automatic relief valve selection, which also offers alternative arrangements to minimize excess area. This is achieved by increasing the number of valves, or using mixed size valves. You can export data to an API or custom format datasheet. The relief valve installation piping can be rated from the inlet to the header, using rigorous dias and other methods, as we presented in the rupture disk module. This allows both the relief valve inlet and tailpipe to be checked for allowable pressure drop. Losses outside acceptable limits are reported, and the pressure profile can be viewed to identify bottlenecks. A separate profile is allowed for the main and supplemental fire valve, if present. Next, we look at the vessel blowdown module, which models depressurization of a vessel and connected piping and equipment. This module calculates the time-dependent depressurization of a system, using component-based physical properties. The depressurization can be modeled from normal operating or during fire conditions. For fire cases, the extent of fire exposure on the vessel can be specified. Horizontal, vertical, or spherical vessel types are all allowed. Piping and equipment connected to the vessel can be included. A detailed time-dependent model of fluid heat transfer and wall unsteady state conduction is used. The wetted and dry walls are modeled separately, since the internal heat transfer coefficients are considerably different. The effects of insulation can be included. All required heat transfer coefficients are calculated when using the standard model. In addition, during fire conditions, the standard API wetted wall heat transfer equations can be used for heat input. Finally, a hybrid model based on API is provided, which attempts to account for both wetted and dry areas of the vessel, but still using heat input as calculated by API. This model reverse calculates outside heat transfer coefficients based on the API wetted area equation. The heat transfer is then calculated as normal. The results will approach API for thin-walled vessels where liquid heat transfer is controlling. Either a square-edged orifice or control valve can be used as the depressurization device. A library of properties for the vessel metal wall and insulation are provided for typical materials. The vessel wall stress during depressurization is included in the calculation. Allowable wall stress data for typical materials is provided in a library, but you can also enter and use material data. This allowable stress is temperature dependent. The calculated time-dependent wall stress and corresponding wall temperature is plotted on the allowable stress chart. This chart allows you to identify a potential vessel wall failure. This is especially important during a fire, where the wall temperature increases with time, and hence allowable stress decreases. This also allows you to determine the required depressurization time for safe operation. By comparison, the typical 15-minute blowdown time requirement used in some project standards is based on values given in the API standards for an assumed wall thickness and material, notably carbon steel, which has a higher allowable stress than stainless steel. It is therefore conceivable that 15 minutes may not be adequate, and our chart will identify these situations. Extensive feedback during solving is shown in chart form. Thank you for watching this video. For further information, please contact our sales team. This video will demonstrate some of flaretot capabilities. It is intended for first-time users, so only covers some of the basics. Flaretot is capable of much more than demonstrated in this video. We will show you how to construct a new Flare network model, as well as import an existing model from flaretot. Also, how to use the relief load calculations to create network case data for pipe network or relief device sizing. Then, how to set up the network cases to define the Flare network loading for design or rating. Finally, how to size relief valves from the case data already entered for the network. To model a Flare network, the procedure is as follows. If you have an existing Flare network model using flaretot software, you can import this model directly into flaretot with a minimum of work. Without an existing model, the network needs to be defined manually as follows. First, you must define the chemical components used in all flow sources. Then, drop network equipment, such as sources, pipes, knockout drums and flares, onto the drawing. Once placed, equipment is connected on screen with the connectors provided. To speed up the process, complicated pipe headers can be created in one step using the Quick Add facility. This creates a header with specified pipe size and material with any number of connections. Tag names are generated automatically from a specified base name. Next, the properties of the network equipment, such as pipes, drums and flares, must be specified by double-clicking on the unit in the drawing. Next, specify flow rates and physical property data for all possible flow cases that may result from each source to the network piping. These cases are usually based on equipment failure or fire, and can be derived from relief load calculations. Finally, network case scenarios are specified as overall combinations of the individual source cases specified previously. For example, a fire case for a particular area would constitute all the fire cases active for sources in that area. First, we show you how to import a flaretot simulation. Note that importing a simulation will always create a new file, so save any work you have open. You need to export the simulation to a XML file using flaretot. Then, this XML file can be imported into flaretot as follows. Using the main menu, click on Import, and then click on Network from flaretot. Select the XML which you exported. Some versions of flaretot do not export all network cases in one file, only the active case. Therefore, you can create multiple XML files if required, with different cases, and import these individually, using this dialog. All our cases are in one XML file, so we click on No to finish the import. The import is complete. We now show you how to set up a network manually. Before defining the network, all chemical components used should be specified. The chemical component list is used for the piping network, all modules, such as radiation and dispersion, and all calculations. A new network is created with typical components already added. These can be changed at any time. Click on Setup. Open the Component Manager by clicking on Network Components. The components already selected are displayed in the Component Manager. In our case, octanol is present in the flare compositions, but is not in the default component list. To add octanol, we locate it in the library components. select one octanol in the library components, and then click on the Add button to add it to our network components. Octanol has been added to the network component list. Now click on OK to save the components. The next step is to create a simple network manually. First, the equipment units are placed on the drawing, and then these are connected. The equipment units that make up the Flare network are selected from the toolbar at the top of the main interface. It is worth noting that if you are only interested in modeling flare radiation, dispersion or noise, and not flare network piping, you only need a simple network without piping. For each flare of interest, only a source and a flare are required. First, we add a piping header with 3 lateral source connections using the Quick Build tool. This tool is located in the Quick Build and Drawing toolbar. We now configure the header arrangement to create in the Quick Build window. Change the number of tailpipes to 3. Change the header base tag name to HDR. Each of the sequential pipes in the header will be given this tag, with a number appended as specified here. In the next step, the location of the header is specified on the drawing. Note that this point corresponds to the red cross on the sketch. Now click on the drawing to locate the header. This point corresponds to the red cross in the previous sketch. If the header extends beyond the drawing size will be increased automatically. Next, the Common Pipe Properties utility opens. Here we specify pipe properties common to the header sections. Note that this utility can be used at any time for any group of pipes. This is a quick way of specifying more than one pipe at a time. Once the Common Pipe class is specified, the remainder of the header pipe section properties can be set. Finally, click on the Apply Changes button to complete the header creation. The new header has been created on the drawing. Now, before adding the remainder of the equipment, we enlarge the view. To do this, click on the Magnify button in the View toolbar. Then, click on the first point of the area to magnify, holding down the mouse button. Then, drag the mouse to the second point and release it. We now place the remainder of the equipment on the drawing. This is selected from the Add toolbox. First, we add a knockout drum, which models removal of liquid as well as pressure drop across the drum. Click on the horizontal knockout drum button. Move to the required position on the drawing and click to place the drum. Now, we add a vertical pipe, which will be the flare stack. Click on the vertical pipe button and place the pipe above the KO drum as before. Note that for both pipes and KO drums, the vertical or horizontal direction refers only to the drawing. Actual arrangement, that is, vertical, horizontal or slope in the case of pipes, is specified in the equipment properties. The drawing orientation can also be changed at any stage in the equipment properties. Now, we add a flare in the same way. Note that there must be at least one flare in a flare network. The flared gas properties are linked into the radiation, dispersion and noise calculation modules. We now connect the equipment units that we have just created. Unused connectors on an equipment unit are shown as crosses, as shown in this example. To connect two units, the connector button is used. The equipment connector changes to green when the connection is allowed. Click to start the connection inlet. Then, move to the knockout drum and complete the connection by clicking on the drum inlet connector. As you can see here, the connection on a vertical pipe defaults to inlet to the top, so the bottom is not allowed as an inlet. Therefore, connect to the top of the symbol for now. We will invert the symbol after connecting. Now, we demonstrate two of the tools used for tidying the drawing. First, we invert the symbol for the pipe to the flare. Select the pipe by clicking on it. Then, click on the X-axis mirror button. The symbol now has the inlet at the bottom. Now, we align the flare stack and flare on the drawing. Select both units by holding down the mouse button at a point above the units, and then drag the mouse to a second point to enclose the units in a selection rectangle. Then release the mouse button. Now the flare and stack are both selected as shown. Finally, click on the vertical align button to align the units. Next, we set the source flow cases and properties for other equipment. The properties for all items on the drawing are accessed by double-clicking on the item in the drawing. We demonstrate with the first source. The first tab contains the description and drawing symbol layout. A tag name must always be provided for all equipment. The orientation section shows a preview of all possible layouts of the symbol, as well as associated text, such as the tag. The current selected layout is highlighted and can be changed by clicking on a new one. The Case Properties tab contains all flows expected from this source. The list of cases is shown in this pane. A minimum of 1 case is required. The data specifying flow rate, physical properties and composition for the case selected in the list is shown here. This data can either be specified or can be linked to a relief load calculation. The data shown in red is required to define the case. Either temperature or liquid fraction can be used to set the stream enthalpy. Chemical composition can be entered in either mole or mass percent, and this can be set as a default for all cases for this source, or specified for each case. Finally, the case type determines the actual pressure for relief device sizing or maximum allowed at the network piping inlet. This pressure is based on the case type and design pressure, as specified in the System Design tab. A case type of none means the pressure given here is the maximum pressure used. To further explain, note that when specifying pressure and temperature, or liquid fraction, this will usually be at normal operating conditions upstream of the relief device. This sets the fluid enthalpy. However, any basis can be used provided the values are consistent. For example, conditions can be specified at relief pressure if known. For either network piping inlet conditions or relief device sizing, the actual pressure for that is used, then conditions are calculated at that pressure, and the same enthalpy as the conditions you specified for the case. Once data has been entered, in this case for the default specified case, the text color changes to blue to indicate data is OK. No further data is required for now. After setting all the source cases, the color changes to blue to indicate they are defined. We set the first tailpipe properties by double-clicking on it. Since the pipe tag is set, and drawing layout does not need changing, we go to the Pipe Properties tab. The piping class must be specified. There are two default classes in a new network. Note that the class is not just the piping material, but also design and manufacturing specifications. These specifications are used to select an appropriate pipe schedule for a given nominal bore. You can also create your own piping classes, including classes with tables of your own allowable custom sizes. We have selected the default carbon steel class. This class is suitable for lower pressure piping using 150-pound flanges, typically used for flare piping. For this class type, nominal bore must be selected. Then pipe schedules available for the nominal bore are shown. These schedules are all those available and not that required by the class. The schedule can be selected manually. We choose Schedule 40 for example. The schedule can also be selected from the pipe class parameters using the Select button. The pipe length must be set. Finally, on the fittings page, outlet fitting must always be specified. This option sets the connection type if connected to a different pipe diameter. If reducer or sharp exit is specified, this will only be modeled if connected to a different size pipe. Outlet fitting type is ignored if connected to a T, as reductions or enlargements are modeled in the Ts themselves. Since fitting type is already set at reducer by the Quick Build Header tool, we just click on OK to save the pipe data. After setting the data for the rest of the pipes, these show as defined on the drawing. Note that only length was required for header sections, since other properties were set as a group by the Quick Build Header tool. A quick look at the properties for the knockout drum show no further data is required. We will only model loss over the nozzles, and not the internals. Therefore the default of 0 for design pressure loss is OK. The nozzle sizes are already set automatically from the connected pipes. We now open the flare properties by double-clicking on the flare symbol. The inlet pipe and nozzle diameter are required. These are entered in the flare tip page. The inlet pipe diameter is the same as the flare stack, so use the Set from Inlet Pipe button. Then specify the nozzle diameter. Open the rating page. The pressure loss characteristics for the flare are specified here. We choose the extrapolation from rated curve method, which is recommended. This uses actual flare pressure loss measurements, which are then corrected for density from the test gas to the actual conditions from the piping network. Properties of the test gas used to make the measurements must be specified. Now we enter the test points, comprising pressure loss at various test flow rates. New points are added by clicking on the Add Point button. The data is entered in the grid. Finally, click on OK to save. The network is now defined and ready to solve. Use the Solve Network button to solve the network. The solving progress is shown in the progress dialog. Key parameters can be shown on the drawing by ensuring the property labels are active. To do this, click on View, Property Labels, Show All. More detailed stream information can be viewed in the Property Summary window. The Property Summary displays physical properties for vapor, liquid and water, if present, for all streams. Pipe sizing criteria is also shown at the base of the report. Flare gas properties are now available to run the radiation, dispersion and flare noise calculation modules. In this section, we will show you how to add another case to a source. This new case will be linked to a gas blow-by relief load calculation. This calculation determines relief flow when a liquid control valve fails open on a pressure vessel. This second case will then be used to show how case management is used. Before any relief load calculation can calculate the relief load, the design pressure of the vessel being protected, that is, the source, must be specified. This is because at relief conditions, upstream vessel pressure is based on the allowable overpressure of design. Note that, in this case, this design pressure refers to the vessel downstream of the failed liquid control valve. Double-click on the source to open the Properties dialog. Click on the System Design Page tab. The design pressure is 30 bar gauge, so we enter it here. The Case Properties page contains the specified and relief load cases. To add our new case, linked to the relief load calculation, click on the Add Relief Load Case button. Select a gas blow-by calculation, and then click on OK, which will open the calculation. The data for the gas blow-by calculation is contained in groups. These are opened by clicking on each of the colored headings in the drawing. These are red one undefined and blue ones defined. Note that the design pressure, as previously set, is shown on the drawing. The relief pressure is based on the case type, which is process, and so is 10% overpressure in this case. First, we open the conditions for the vessel upstream of the control valve. The pressure, temperature and composition is required. Note that the specified composition can be that of the vapor, inlet fluid or the liquid in the vessel. However, a flash of this composition at relief pressure must result in some vapor, which forms the basis of the relief load. Invalid data is shown in red and changes to blue once defined. To close and save this data entry, click anywhere on the drawing. Now we specify the control valve by clicking on the label. We first set the tag name. Then, we derive the data for the control valve from the typical control valve database. Data for a 4-inch globe valve with single port and linear characteristics is used. We will allow for a control valve bypass valve being fully open, as well as the control valve failing. You can include a bypass valve by clicking on the checkbox. Then, click on the bypass valve label to enter the valve properties. A generic 2-inch globe valve will be selected. After specifying 2 inches for the nominal bore, the data required is derived from the database, so no further data has to be entered. All required data is now specified, so that the relief load can be calculated. Click on the Calculate button. The results are shown in the Calculation Results window. These can be printed or exported from this window. After this window is closed, these results are ready to populate the case data in the source. Close the blow-by calculation and save the results using this button. The case load data has now been populated by the linked relief load calculation. Change the name in the name field to indicate that it is a blow-by case. The name changes in the list automatically. Click on OK to close and save the source data. We are now ready to set up an example network case using this new blow-by source case. Open the Case Manager by clicking on the Case Manager button. The lower grid shows all possible contributing sources to piping network flow. The columns in this grid correspond to the source case index, which is active in a network case. The upper grid shows all the network cases or scenarios. These network cases are typically a plant shutdown, or a fire, or plant power failure, for example. First, we add a new network case, which will comprise blow-by from the first source. That is, only the one new source case will be active. This is only an example, as typically, multiple source cases would be active in a network case. Use the Add Case button to add the network case. Then, rename it to Case 2, Blow-by. Then, set the blow-by case from the first source as active for this network case. To do this, click on the Contributing Elements grid on the first source row and case to column. Then select the blow-by case. The grid now shows Case 2 is active. The new network case is complete, so close the Case Manager. Select the new blow-by case as the active case by clicking on the Select Case button. You can now see that only flow from the first source is active, as the other sources are grayed out. The network case that is active is shown in the status bar. We run this case by clicking on the Solve button. Now we explore relief valve sizing. We use the first source in the network piping, and will size the relief valves based on both source cases, which are already defined. Open the properties of the source by double-clicking on it. Change the source type to Relief Valve. The Relief Valves tab is now visible. Now, open the Case Properties page. Case 1, Design, has a case type of None, and it is a relief valve sizing case. The conditions provided are at normal operation. The None overpressure option, which is the default, implies that the case pressure is already at relief. Clearly the normal operating pressure of 20 bar will not lift the relief valve, since the design pressure is 30 bar gauge. We change the overpressure type to Process, which is equivalent in this case to blocked outlet. The stream pressure will now be set to 10% above design when sizing the relief valve. Move to the Relief Valves tab. The maximum tailpipe outlet pressure, based on all network cases, is required before the relief valves can be calculated. select balanced bellows as the relief valve type. Then click on the Size button to size the relief valves. The results window is then displayed. This shows all available relief valves that can be used for the design pressure and service temperature. This also shows sizing calculations for all cases and all selected sizing methods. Finally, configurations which meet required duty are shown. This can include alternative configurations that minimize excess area, if specified. Namely, those with mixed valve sizes, or more than the minimum number required, with a smaller orifice area. After closing the results window, the configuration with smallest excess area of selected configurations is set in the installed valves. This is because we have selected the relief valve selection as automatic. You can also select the Use Installed Valves option and specify the actual relief valve installation. Then the calculation will rate the installation instead of sizing it. For example, we will select two valves, one with a P orifice and another with a N, and then rate this installation. First, we change the relief valve selection option to Use Installed Valves. Then we change the valve that is already in the installed valve list. This was added by the previous sizing calculation. Click on the size column for the valve, and change it to an N orifice from the list of allowed valves. Then click on the Add Relief Valve button, and select P for the orifice size. Now we can rate the installation by using the Calculate button again. The installation is adequate. Close the Source Properties dialog by clicking on OK. Finally, note that the drawing symbol has changed to a relief valve. That completes this brief introduction to flaretot network piping design, case management and relief valve sizing. This tutorial will demonstrate how to import stream data from a PetroSim database. To show you how it is done, the stream data for some flare network relief valves will be imported. Two sections of a plant are considered. These are the oil and the NGL stabilization sections. The two sections have been modeled in two separate cases using PetroSim. The stream data has already been exported into SQLite database using PetroSim. We will import stream data for 3 relief valves located in the oil stabilization train. First, the blocked outlet sizing case data is linked to the vapor outlet stream in the simulation. Then, the fire case is linked to the inlet two-phase stream for composite vessel fluid properties. Only one case is demonstrated, for the deethanizer, in the NGL stabilization train. The stream detail is located in the subflow sheet, COL2. The relief case data is linked to the column vapor outlet and defines the case for protection against condenser failure. The chemical components used in any stream data imported from PetroSim must be present in the flaretot network. Standard library components that are missing in the flaretot network will be created automatically on import. Hypo components need to be defined in flaretot before import, using the same name as the PetroSim simulation. In this demonstration, Hypo 1 is missing. We will first create this component before proceeding. On the main menu, click on Setup. Click on the Network Components menu. Click on the Create New Component button. Set the component name as Hypo1* to match the PetroSim data. Set the normal boiling point to 350 Celsius, the same as PetroSim. Change the molecular weight specification to specified. And set the molecular weight to 280, the same as PetroSim. Use the Estimate button to estimate specific gravity. This is not the recommended option, but will suffice for this demonstration. Click on OK to proceed. Click on OK to save the component, and return to the component list. Hypo 1 has been added to the component list. Click on OK to proceed. Now we set up the cases in the flaretot network, so we can import the stream data. This only needs to be done once. If PetroSim data is revised, data can be imported again. The oil stabilization relief valves each require a new fire case. The default design case can be used for the blocked outlet. The NGL stabilization relief valve condenser failure case can use the default design case. We first set up PSV1 by double-clicking on it to open the Properties page. Select the Case Properties page. Change the default case name to Blocked Outlet. Add a new relief load calculation case, which will be the fire case. If the design pressure has not been set, the calculation will not be opened, as in this case. You should set this on the System Design tab before proceeding with import, or the relief load will not be automatically calculated on import. Click on OK to proceed. Rename the case to Fire Case. And then click on OK to save the case data and return to the drawing. Repeat setting the cases for PSV 2 and 3. We are now ready to import the PetroSim stream data. Click on the File menu. And then Import Stream Data. You will see the flare network sources displayed, ready for mapping to the PetroSim stream data. Open the PetroSim database by clicking on the Database button. Note that, once opened, the database name is saved with the network, and will be automatically loaded when this form is opened again. You can still change it at any time. The simulation case list displays the cases present in the selected PetroSim database. The active PFD list displays the process flow diagrams for the selected case. If marked as active, the streams in the PFD are included in the PetroSim streamer list. The PetroSim database streams that can be mapped are displayed in this list. When a stream is selected in the list, the stream data is displayed in the Stream Data panel. Now select the Component Mapping tab to check chemical component mapping is correct. The default mapping is already correct, so does not need to be changed. Mapped library components, which are already used in the network, are shown with this symbol. Those that will be added are shown with this symbol. These are only added if an imported stream requires them. Note that the Hypo1 component has been automatically mapped by name. Now we define the flaretot to PetroSim stream mapping. To expand the cases for PSV1, we click on the plus symbol in the list. Repeat this for PSV2 and 3. Deselect the NGL stabilization case, so that only streams in the oil stabilization section are shown. Select the Stage 1 vapor stream in the PetroSim streamer list. Click on the link icon for PSV1 blocked outlet case to map the PetroSim stream to this case. The blocked outlet cases for PSV1 and 2 are then linked by repeating this process. The fire cases are mapped in the same way, that is, by again selecting the PetroSim stream and clicking on the link icon. Now to map the relief valve in the NGL section, we need to select the NGL case. To make it easier to find the required stream, deselect the oil stabilization case. Finally, map the oil stabilization relief valve using the same procedure as before. All required stream cases are now mapped to the PetroSim streams. Click on the Import button to import the data. The mapping data can be saved so that all component and stream data links will be maintained when the import dialog is opened again. This means these do not need to be defined again. Click on Yes to save the mapping data. Note that two-phase stream temperatures may be adjusted to maintain vapor fraction using the flaretot physical property module. This adjustment should be small, but ensures the enthalpy basis is the same. Any required adjustments are reported before the import dialog is closed. The data has now been imported. Any relief load calculations, in this case the fire cases, are automatically rerun so that the revised load to the flare is calculated. Note that required additional data in the source, such as design pressure, must already be defined for this step. If the PetroSim simulation is revised, the data can be imported again using the import dialog. This is a one-step process since mapping data does not need to be defined again. This video will show you how to size a rupture disk installation using flaretot. When sizing a rupture disk, the entire installation is examined, from the inlet vessel or equipment to the atmospheric vent or outlet flare header. The installation is considered adequate when one of two conditions is met. 1. The calculated flow rate for the installation is greater than the relief flow rate when the inlet pressure is at allowable overpressure. 2. The inlet pressure is less than the allowable overpressure at the required relief flow rate. Both criteria are evaluated in flaretot, depending on which calculation method is used. Rupture disk calculations can be contained in network rupture disk sources or standalone calculations. We will first show you how to create and access a source rupture disk calculation. Then we will carry out a detailed standalone calculation. To create a network rupture disk source with an associated calculation, we first need to change the source to a rupture disk. Note that we have used the tutorial 8 flaretot file provided. First, open the source properties by double-clicking on it in the network drawing. Now change the source type to a rupture disk. The source symbol changes to a rupture disk, and the rupture disk calculation page is now visible. This rupture disk calculation page is the same as used for standalone calculations. The only difference is that some parameters such as tags and design conditions are shared with source properties. Now we will create a standalone calculation and complete the rupture disk sizing. We first need to add a standalone rupture disk calculation. Click on the Rupture Disk Calculations button. This opens the Rupture Disk Standalone Calculation Manager. Click on the Add button to add a new calculation. The calculation is identified by the rupture disk tag, which has not yet been defined. Double-click on the calculation in the list to define and calculate the installation. We are now ready to define the details of the rupture disk installation. Our example rupture disk installation protects a vessel with a design pressure of 12 bar gauge. It is designed to ASME 8 code. As allowed by this code, the installation has both a main and a supplemental rupture disk. The main rupture disk protects against process overpressure, while the supplemental disk protects against exposure to fire. First enter the installation descriptive data and the design pressure. The defaults for the design code and disk arrangement do not need to be changed. These default to ASME 8 and single set pressure. Now we define the rupture disk installation arrangement from the piping layout. In a study phase, this would need to be estimated based on preliminary equipment and flare header locations. This drawing shows the dimensions of the rupture disk installation. Note that it is also included with the tutorial documentation. First define the main rupture disk arrangement. Go to the main rupture disk page. New calculations have a default arrangement. This arrangement can be changed to the required layout. The default consists of a vessel entrance, a vertical pipe, rupture disk, another vertical pipe, a standard 90-degree elbow, and a horizontal pipe, which connects to a header. The entrance, exit and rupture disk are required and cannot be deleted. Enter the vessel tag in the equipment tag field. Now set the corner radius by clicking on the corner radius options. The vessel exit is rounded, and has a corner radius to pipe diameter of 0.02. Select the connecting vertical pipe. We have overlaid a reminder of the pipes section that this represents. As a preliminary estimate of the installation size, we have selected 3-inch. Select carbon steel as the piping class. Set the nominal diameter to 3-inch. Our pipe class gives this as Schedule 80. Finally, set the length to 1.5 meters. Select the rupture disc. The default coefficients for the coefficient of discharge and velocity head loss methods are used for this demonstration. Manufacturer values should be used if available. The rupture disc diameter will be set from the connected inlet pipe, which is the default. Select the next piping element. Complete the details as before. For this and remaining pipes, the piping class requires Schedule 40. The fitting in the default arrangement is a 90-degree elbow. We need to insert a vertical pipe and T-fitting with flow through the run of the T. Click on the Add Fitting button to add a new fitting above the pipe. Change the new fitting type to a T with flow through the run. Change the nominal diameter to 3-inch. The default NC class of 150 pounds does not need to be changed. It will be used to calculate the inner diameter. Now add a new pipe above the T by clicking on the Add Pipe button. Set the pipe data as before. A new pipe defaults to a horizontal orientation. Change the inclination to a vertical upwards pipe. Note that the symbol in the list changes to indicate the inclination. Select the next piping element. This is the 90-degree elbow added by default. Change the size to 3-inch. Select the next piping element. Complete the details as before. Select the next piping element. Enter the maximum pressure expected in the flare header at the tailpipe entry point. This is 1.5 bar in our example. Also, set the optional description. The installation has a supplemental rupture disc for fire, so tick the supplemental disc checkbox. The supplemental fire disc arrangement page is activated. We now define the supplemental rupture disc arrangement as before. The arrangement is shown above for reference. To proceed, we need to add the sections shown above, namely, a T-exit, a vertical pipe, an elbow and a horizontal pipe. Click on the Add Fitting button to add the T. The new fitting defaults to a 90-degree elbow. Change this to a T, with flow through the branch. Set the nominal diameter. Now add the vertical section of pipe by clicking on the Add Pipe button. Complete the details as before. The default for a new pipe is horizontal. This section is vertical, so change the inclination to vertical upwards. Now add a 90-degree elbow by clicking on the Add Fitting button. The fitting type defaults to a 90-degree elbow, so only the nominal diameter needs to be changed. Add the final horizontal pipe by clicking on the Add Pipe button. Complete the details as before. Finally, select the header exit. Set the outlet pressure to 1.5 bar. Both the main and the supplemental rupture disc installations are now defined. Now the sizing relief cases need to be defined. Open the Relief Case Properties page by clicking on the Case Properties tab. By default, the calculation already contains one design case, which is undefined. The normal flow conditions to the vessel are shown here. This data is also provided in the tutorial documentation. For our example, we have two relief load sizing cases. There is a process blocked-in case, with only the vapor flow to be relieved. Properties for this case will be manually specified. There is also a fire case. The properties for this case will be determined using a fire relief calculation. flaretot will automatically use the process case to size the main rupture disc, and the fire case to size the supplemental fire disc. First we define the process case. Enter a description. Set the case type to process. This ensures that the conditions at relief will be calculated at 10% above the design pressure. Enter the vapor mass flow. Enter the temperature and pressure at normal conditions. The actual temperature and pressure at relief conditions will be calculated from these values using constant enthalpy. Enter the composition of the vapor. The process case is defined. Now add a fire relief load calculation by clicking on the Add Relief Case button. Ensure the fire calculation is selected and click OK to create the calculation. The default vertical vessel type and ellipsoidal heads are OK. Enter the inner diameter and tan to tan height. Select the Fluid Properties page. The normal operating conditions in the vessel need to be specified. The conditions at rupture and relief overpressure are calculated from the normal operating conditions, based on constant volume with heat input. Enter temperature and pressure. The vessel has a hydrocarbon liquid normal operating level of 1 meter. This affects both heat input and time to reach rupture pressure. Click on the liquid present checkbox and enter the liquid level. Now enter the total fluid composition based on the fluid flow to the vessel. Click the flash button to flash the fluid and display the vapor and liquid compositions. This is not required for the calculation to proceed, but is provided for information only. Now select the Calculation Options page. Select the Advanced Relief Load model. This model calculates heat transfer coefficients for wet and dry areas. Enter a vessel wall thickness of 20 mm. The default thermal conductivity is acceptable. Click the Calculation button to calculate the relief load. The results page is shown. Note that in this case, the design or rupture pressure is reached in 41 seconds. Results can be printed, saved or copied to the clipboard here. Close the results page. Save and close the calculation, which sets the relief load properties in the rupture disk case properties page. Select the rupture disk calculation page. Select the Calculation Options page. Both the coefficient of discharge method, termed KD, and the velocity head loss method, termed KR, are selected by default. The KD method only rates the rupture disk as a nozzle, and does not model the surrounding piping. The method is approximate, and only applicable for certain piping arrangements. We do not use it here. Therefore, deselect the KD method in the sizing calculation methods. Select the KR Options tab. This page gives the methods used to calculate the pressure drop over the rupture disk and piping. The default options do not need to be changed, but so you understand their usage, we will discuss them briefly. Firstly, more than one method is allowed for a given phase, so results can be compared. Also, a method is only used if the fluid phase matches the method. For example, the incompressible method is only used for liquid fluids. The API method is not selected, as it is approximate, for example assuming a specific heat capacity ratio of 1.4. Use it only if required by project standards. The Lappel method uses analytical, adiabatic equations, and a calculated specific heat capacity ratio for each section. It is fairly accurate and convenient for vapor phase fluid, as it is much faster than Dyer's. Finally, the Dyer's method can be used for all phases, including two-phase, vaporizing liquid and retrograde condensation. Dyer's is the most accurate method, but will take the longest to calculate. The default two-phase hold-up methods represent the most conservative, that is, using calculated hold-up for inclined upward pipes only, and no slip for other inclinations. Now run the installation rating by clicking on the Calculate button. The sizing results are shown in a new window. The main rupture disk installation is rated using the process blocked-in case. A small amount of liquid is produced when the vapor is compressed to relief overpressure, and thus the Dyer's method is used for rating. The calculated pressure in the vessel exceeds maximum allowable, and thus the installation is undersized. The supplemental fire rupture disc installation is rated using the calculated fire case. The fluid phase is vapor, so that both the lapel and the Dyer's method are used for rating. Both methods show that the pressure in the vessel is less than allowable, and thus the installation is acceptable. There is close agreement between the two methods. After closing the results form, you can view the pressure profiles across the installations to determine if there are any bottlenecks. The maximum allowable relief overpressure and the pressure profile calculated using Dyers are shown. It can be seen that the pressure exceeds allowable at the T-fitting. Note that, if optional tags, such as pipe tags, are set, they will be displayed instead of the item label. Now display the supplemental rupture disc installation profile. The profile for lapel and Dyers are very similar. The pressure is always less than allowable, so the installation is acceptable, and possibly smaller piping may suffice. We now revise the installation piping, nominal bores. We will change the main installation from 3 to 4 inches, since the pressure drop is too high. In addition, we will change the supplemental installation from 3 to 2 inches, to see if this meets the required maximum pressure. This is also the smallest size we are allowed in our project spec. First, change all main rupture disc elements to 4-inch. Now change the supplemental rupture disc elements to 2 inches. Remember to change the shared piping section to 4 inches. Click on the Calculate button to rate the installations with the new sizes. Now both the installations are acceptable, since the calculated vessel pressure is less than allowed. The final installation is shown here. This completes the rupture disc tutorial.